All right, back down on the glass again, because I want to talk about one other really critical aspect in our early work in interpreting NMR spectra, and that is integrated proton spectra. This is the stuff that tells us that how many hydrogens are in each group that we see in an NMR spectrum. I'm going to use this really simple example molecule, just simply something like ethyl chloride, where looking at the structure, we have two groups of protons, the methyl group here, CH2 group there. So we're going to get an NMR spectrum that has two resonances, two signals in it. Now, later, I promise later, we will talk in great depth about where these signals are, the fact that one of them is at 1 ppm and the other is at 4 ppm. The chemical shifts, we'll talk about that. The fact that this one is a triplet and that one is a quartet, we're going to talk about that too. But in trying to manage the fire hose of information that is learning how to really interpret NMR spectra, we're taking it just a piece or two at a time. And so we're going to focus now on the fact that there are just simply two resonances and their integrations. The fact that this resonance has three hydrogens in it. This resonance, this group, represents two hydrogens. So we take this simple little molecule and define, for just a second, what we mean by integration. And that is simply counting the number of hydrogens in each of these signals. Now, integration is a property of only proton spectra. We don't do that in carbon-13 NMR spectra typically. And there's very good reasons for it, and yes, we'll talk about that too. But for right now, integrated spectra is almost exclusively referring to, for our purposes, proton NMR spectra. In order to understand how we integrate these things, how we gather from the spectrum the information that this group has three hydrogens in it, this group has two hydrogens in it, it really is a good idea to have kind of an idea in our head of how an NMR spectrum is actually represented in the computers that do all of this work, that help us do all of this work. And essentially, when you acquire an NMR spectrum, ultimately what is in the computer is simply a mathematical representation of the frequencies. It can be represented this way as a function, okay? Literally a mathematical function of the frequency. So when plotted, it is 0 here, it goes up and down in this region, is 0 again, goes up and down in that region. So this is literally a plot of a mathematical function. And when I first obtain spectra, if I see this show up, let's say in the computer display, when I first run this molecule, I will look at it and say, oh, look, I have two resonances. There must be two groups of distinct protons in this thing. But now I want to count the number of protons within each group. What you do is you literally integrate the spectrum. You tell the thing, start here, let's say at 4.2, and go down to here, and I'll just mark it as 3.8. You literally mathematically integrate, definite integral, from 4.2 to 3.8, that function. Okay? So you carry out mathematically this process. Now, it's a numerical method of an integration, Newton's method or something. I don't know exactly what algorithm the computer uses to do it. To be honest, I don't particularly care. I will trust my computer science colleagues and my mathematics colleagues to get that part right. But what it will do is it will come back and it will give me a number. And the number will be, some number. Let's pretend for a moment it comes out like this, 0.022. It's very unlikely it's going to come out at the moment to be a nice, pretty whole number. Maybe a large number, maybe a small number. It doesn't matter. It comes out with a number. So I make note of that. Then I tell the computer, do exactly the same process, but now over here. And you start on the left side of the peak, let's say about 1.2, and you say, go over to the right side of the resonance, or the group of peaks, let's say 0.8. And so it will literally do another integration, exactly the same functions, as it is the same spectrum, but now the limits of integration have changed. And it will do another numerical method integration and come out with a different value. And let's say this one will come out with 0.033. Now, this is what the computer will come back mathematically, but this is where our intuition as chemists starts to come into play here. Because while mathematically the integrated values may come out like this, we understand they represent number of hydrogens in each group. And those numbers are whole numbers. So we scale these numbers to the nearest whole numbers. And furthermore, and this is what you start to learn as you interpret many spectra, groups that show up in this area with a chemical shift, we call it, of around 1 ppm, are often, it's not a guarantee, but are often methyl groups. Okay? And so I'm going to use my chemical intuition and say this integration around 1 that came out to this value probably actually represents 3, a methyl group, a group with 3 protons in it. I tell the computer, scale these integrations to that value. And the computer will say, okay, if what I came up with, 0.033, is actually the round number 3, I'll apply the exact same scaling to this value, and it will come back with the value of 2. And there are my nice, pretty whole numbers. You will usually see them displayed in the spectra that we're going to make use of, usually as a number printed below the peaks, often with a little bit of a line on them to indicate the range that you actually did for integrating. So it'll look something like that in the spectra that you see. And there it is, the classic 3:2 ratio, representing 3 protons in this group, 2 protons in that group. Pretty straightforward. Now, in reality, when you see these 3 and 2, yeah, those are idealized numbers. In reality, if I tell the computer, call this one 3, it will come back, and it will probably come back with 1.98, 2.02, or something. So in our heads, yes, we do round to the nearest whole number, and it's usually pretty simple to do. Okay? Now, I do want to point out one other potential complication here, and that is, imagine this molecule, diethyl ether. If you ran this molecule in an NMR spectrometer, got the proton spectrum, to be honest with you, it would look much like this one. It would be hard to tell the two apart. This molecule is symmetric, and as we've talked about, that is going to give it only 2 groups to look at. So we will get a spectrum that has 2 groups, and their chemical shifts will be close to where these are. If you then integrated, you would come up with the same 3:2 ratio that the ethyl chloride gave us. But we have to realize 3:2 is the smallest whole number ratio. What this really would be is 6:4. Okay? 6 protons total in this group on opposite sides of the mirror plane, 4 protons total in that group on opposite sides of the mirror plane. So be cautious when you're interpreting NMR spectra. Integrations are very nice, but realize that when you get the smallest whole numbers like 3 and 2, it could be 3 and 2, just like it was here. It could be 6 and 4. It could be 9 and 6. It could be any set of whole numbers that preserves that ratio. As a reminder of this kind of thing, way back in general chemistry, back in the good old days, you learned about empirical formulas versus molecular formulas. And one classic example is this, CH2O. That is the empirical formula. And it gives you the smallest whole number ratios of the atoms in the molecule. Equal numbers of carbon and oxygen, twice that number of hydrogen, C1H2O. But there's actually a whole series of molecules that have that empirical formula. A classic one that everybody is familiar with is this one, C6H12O6. That's the molecular formula of glucose. and realize it has equal numbers of carbon and oxygen, twice that number of hydrogen, it has the same ratio. This is the smallest whole numbers. This is the actual formula, okay, the actual molecular formula. So how do you tell the difference? That can be a bit tricky sometimes. There are other things to look for. And as we move along this semester, we'll see some of the other things that can clue you in that while you measured a simple 3:2 ratio, the actual integrations might be, not 3 and 2, but 6 and 4. One of them can be a measurement of a molecular weight. If you have a simple ratio here, but the molecule seems to be kind of large, that it can be an indication that the molecule, it has some symmetry in it, but it's larger than the initial ratio led you to believe. So there it is, integrated proton spectra. This is a very powerful, very useful tool, and together, as we'll see in this module, with just the information of number of groups in the proton spectra, number of carbon groups in the carbon spectra, and for your proton spectra, the integration numbers, you can learn an awful lot about chemical structure from just that bit of information. It's your first sips from the fire hose of information that NMR spectroscopy gives us. Okay, so keep that in mind, practice a few of these, and talk to you later.